Okay, we've looked at free fall, we've looked at pendulums. Now we're going to look at roller coasters. Let's talk about roller coasters. First thing we want to do is talk about the energy types. Same three types of energy: kinetic, potential, or both. Let's talk about energy types here at this roller coaster. I want you to do that first. Look at these positions, writing. 1, position 2, position 3, position 4. You pause the video and make the decision about what kind of energy this roller coaster has at each of those locations. Go ahead and do that now. All right, so at the top, if you've ever been on a roller coaster, you know that one thing they do up here at the top is they stop for just a minute, just so it's real scary, you know? So since we're stopped, we don't have any kinetic energy at the top. At the top, we're gonna start with all potential energy because we have all height there and no speed yet, right? Then we get this little nudge and we start to go down the hill, right? Number 2, what kind of energy do we have? Well, do we have height right here? Yes, we do. So we definitely have some potential energy. Do we have some speed right there? Yes, we do. We definitely have some speed right there. That's when you're freaking out. So you have both kinetic and potential right here in the middle of that hill. At the bottom down here, what kind of energy? You might notice that on this particular ride, this is the lowest possible point. At the lowest possible point, the height is 0, which means we have no potential energy, which means that all of this potential energy, all that energy we started with up there, has all been converted into kinetic energy at the bottom. You should be seeing a pattern right now where we have potential at the top and kinetic at the bottom. This one right here always trips people up. What kind of energy here? A lot of people say it's all potential because their reasoning is, well, it's at the top of the hill. Yes, but it's not at the top of the highest hill. Do we have some height here? Yes, we do. It's definitely higher than the lowest point. So back that up. We definitely have some potential energy for sure. But is this roller coaster moving? I certainly hope that it is. Because if it's stopped, then this is where the ride ends. We want to finish the ride. We want to go on to the end. So there's also speed here as well. So we have potential and kinetic energy. But here's the point. Here's the reason I know that it's not stopped. It hasn't gone all the way back up to this highest possible height. So since we haven't lost all of that kinetic energy, it's still going to retain some of it, right? So we have potential at the top, kinetic at the bottom, and check it out. Do not use the shape of the roller coaster at any location to try to determine what kind of energy it is. It's very simply all potential at the top. It's very simply all kinetic at the bottom, and everywhere in between those two locations, doesn't matter what the roller coaster looks like, it's got both potential and kinetic energy. Let me compare these three situations. Look, we've now had roller coasters, pendulums, and free falls. Check it out. With a roller coaster, we had all potential at the top. Free falls, all potential at the top. And it doesn't matter whether we're throwing something up or if it's dropping. We start with potential energy on the way down. We end up with all potential energy if we threw something up. Pendulum, highest height, we have all potential energy. At the bottom, all kinetic energy for a pendulum. For free falls, at the bottom, we either start out with all kinetic energy or we end up with all kinetic energy if it's dropping, if it's falling. Roller coaster, lowest possible height down here at the bottom, all kinetic energy. And whether we're talking about roller coaster, free fall, or the pendulum, at all of these locations in between, we have both potential and kinetic energy. Start to see a pattern, right? So roller coasters, all potential at the top, free fall, potential at the top, potential at the top. At the bottom, it's all kinetic energy. Everywhere in the middle, doesn't matter what it looks like, as long as it's got both height and speed, both forms of energy are going to be going on. So that's how all three of these fit together. So last practice problem here. Let's go ahead and solve a problem with a roller coaster. But it's going to be the same, y'all. It's going to be the same kind of problem. The highest hill of a roller coaster is 20 meters higher than the lowest point on the ride. So if we simply draw our little roller coaster right here, they're telling us that this is a height of 20 meters. That's where we're going to start. That's where you start every roller coaster ride. 20 meters above that lowest point. If a roller coaster starts from the top, that's what we're saying right here, right? So we're starting up there, that's our EI. How fast will it be going when it is 5 meters above the lowest point? Notice it's not at the lowest point. It's not right here. That's not where it's at. It's somewhere 5 meters above the lowest point. I should put that down here. Let's just throw that point right there, right? So that's going to be our EF point, where the height is 5 meters. What do they want us to find? How fast will it be going at that point? Once again, just like a previous one we found, we want to know the speed here, and it has some height there. If it's got speed and height at the same time, guess what? It's going to have both kinetic and potential energy right there. If it's at the bottom, it would be all kinetic, but it's not. It's not at the bottom. It's 5 meters above the bottom. At the top, EI, we start out with all potential energy. So here we go. We've done one like this before. A little tedious, but not impossible. EI equals EF. We always start here. EI is potential energy, MGH. EF is potential plus kinetic, so MV squared over 2 plus MGH. It doesn't matter what order you put these two in, as long as they're both there and we add them together. Remember, they got to add together to equal the total. Once again, don't care about the mass. Do not care about the mass. Let's go ahead and plug these numbers in. G is 9.8. Our initial height is this one up here, which was 20. We want to know the speed. G is 9.8, and our final height, the height over here, was 5. All right, so let's do a little simplification. We got 9.8 times 20 to begin with, and that gives us 196 for that, equals V squared over 2, plus 9.8 times 5 is 49. All right, algebra. Got a few algebra steps here to do. Like, check it out, guys. We have done all of the physics on this problem. If you goof up from here on, you still get 3.5 points as long as I see all this. Subtract the 49 first from both sides. 196 minus 49 gives us not 4, minus, not divide. 196 minus 49 is 147. Multiply by 2 to get the 2 out of this denominator right here. 147 times 2 is 294. Do we have 294 before? I don't remember. V squared, last step is going to be to take the square root. And the square root of 294 is 17.1. 17.1 meters per second at this point right here. It's going to continue to go faster after that, but at that point right there, it's moving at 17.1 meters per second, right? I want to once again tell you, all that from there up is physics. Everything from, well, no, from here up is physics. Everything from here up is physics. Everything from there down is algebra. I give you points for algebra, but this is not a math class, right? So this is not the stuff I want you to focus on. It's everything else for this whole problem, and I shouldn't have done that right now. Let me get rid of all those lines. That's kind of fun, though. So this, again, is one of the harder types you'll have where you have one form of energy equals both. All right, so there's your roller coaster problem.